right, a fair number of questions this morning. So I'll start with ones I got by email. If you're here for the chat, just post the chat, and hopefully I'll be done soon enough for you. All right, so first question is addressing the organic homework, and the question is: you're given the formula of an alkane is C4H2N plus 2 for an alkane, and you're asked to find what's the general formula for something with a cycle or that has a ring in it. So let's start out with something simple. This is a C6 membered ring, and let's draw in a couple hydrogens here. So if we look at this formula, we have 1, 2, 3, 4, 5, 6 carbons, and we have 2, 4, 6, 8, 14 hydrogens. So this is our C6H14, which corresponds to our C4H2N formula. So how about a ring? Well, with a ring, we have C6, 2, 4, 6, 8, 10, 12. So the difference here is that we've got a difference of 2. And where that 2 comes from is 2 hydrogens are popped off. Basically, these are popped off in order to form a bond between the carbons. So if we're looking for the general formula for a ring, it's C4H2N. Alkene is going to follow the same line of reasoning. So if we have an alkene, in order to get this double bond, we have to take 2 hydrogens off and form a bond. And so for an alkene, we're also going to get C4H2N, assuming that we have a simple alkene. Now this is going to show up when we're doing hydrogen uptake analysis. So with hydrogen uptake analysis, what you do is you measure the formula of your compound. Let's say you get something like C6H12. Well, do you have an alkene or do you have like a cycloalkane? To do this, you measure hydrogen uptake. If it's an alkene, it will absorb hydrogen. If it's not an alkane, it won't. So that's how you do those problems. Second question comes from, and actually pretty much the next 2 questions are all going to come from the lab the organic students did yesterday. And these are questions about doing the stereochemistry of rings. So first question is number 5 on page 15, which is make line bond drawings for the Fischer projection of the various stereoisomers of 1,3-dimethylcyclohexene. So cyclohexane is this formula. The hex is 6. 2 methyls, that's where the dimethyl comes from. So as a first pass, what we're going to do is we're going to draw out wedges and dashes. The easiest thing to do is start with 2 wedges. Now the question is, are these chiral centers? And if you count them up, they are. There's a hydrogen, there's a CH3, there's a branch ring this way, and there's an unbranched ring to the left. So these are definitely two stereocenters here. But the question is, are these meso or are they not? And if you look at it, it's definitely a meso complex because you've got this mirror plane represented by a sigma where the 2 planes reflect. So this is actually the meso form. You only have to draw this one. So if both sites are the same, both are up or both are down, they're the same compound, even if they're both up or both down, because they're superimposable. They're their own enantiomers. And if you work it out, one of these is going to be R and the other one's going to be S. For one up, one down, we don't see this mirror image anymore. And so because there is no mirror image, both of these are going to be R or both of these are going to be S. And that means that we can do 2 other isomers. Mess that one up. Or we flip the up and the down. So these 2 are enantiomers, and this is an enantiomer with itself. So for number 5 on page 15, this is the answer. These are the only 3 possibilities you get. Now, some people will try to draw this. If you have one or the other, your answer is correct. But if you have both, so you have both the wedges down and both the dashes, one of those is incorrect because they're the same compound. You're being asked to draw the unique stereocenters. So for definitely number 5, you should only have 3 final answers when you get done. And one is the RS with the 2 centers, and the other is both R, both S. Moving out, clearing out my email so it's a little bit easier to see what questions are being asked. So question 8 on the same assignment. So you're given compound that is R, 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 and you're asked to figure out, first of all, how many different possible stereoisomers there are, as well as write out what they are and pair up the enantiomers with the diastereomers. So, off the bat, we're going to, when we start, so let me give you a little context. When we start talking about alkanes, let's say we have something that has 4 stereocenters. 1, 2, 3, 4. Fluorine, chlorine, bromine, iodine. We have 4 stereocenters. And we would name this 3, let's say these are all R. I don't actually know. So let's say they're all R. This would be 2R, 3R, 4R, 5R, whatever the name of this compound is. And so this is kind of building you up to this when we get to alkanes. So if you can identify it as R or S centers, the naming gets really easy. So this is kind of approximating this. So let's say you have some unknown compound with 4 stereocenters, and we're going to assume here that you can't generate any meso complexes. Well, what are all the different combinations? Well, the enantiomer here is going to be the one that's flipped. So we have 4 stereocenters, 2 to the 4th power. That's 2, 4, 8, 16 combinations. So anything where all the centers are back and forth, these are enantiomer pairs. And then you just start iterating all the different combinations. So we have R, 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 S, R, R, S, R, R, S, R, R, S, R, 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 S, S, R, S, R, S, R, S, S, R, S, R, R, S, S, R, S, R, S, S, R. And with each of these, you do the enantiomer pair. So this enantiomer pair, S, S, R, S, R, S, 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 R, S, R, S, 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 R, R, S, R, S, R, S, R, R, S, S, R, S, S, R, R, S, R, S, R, R, S, S. So we have 1, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 so far. So some of these are actually redundant. Yep, this combination here is redundant. 16. So I need to go figure out where the redundancies are. But basically, this is all you're going to do is start iterating through. So, but these are enantiomer pairs. These are enantiomer pairs. These are enantiomer pairs. These are enantiomer pairs, and so forth. Everything that isn't boxed out here is your diastereomer. So that's how you can work out the last one. Start out with your 4 R's, write out the enantiomer, and then just start iterating all the different combinations of R and S. So the first one is an S, second is an S, third is an S, fourth an S, then 2 of them are S's, and 3 of them S's, or 4 of S's. 4 of them are S's. Now, if you constantly do these enantiomer pairs, you're going to quickly exhaust all the combinations, which is what I would recommend. So do one, change it, find its enantiomer, change it, find its enantiomer, change it, find its enantiomer. And then when you're up to 16, you'll know you've done it correct. You know that you've worked them all out. Now that was it for questions I got asked in advance. For those of you who weren't able to, for organic, that weren't able to get through more than the first or second problems, there is one thing I need to note about problem 4. And it's not hard, it's just one of those little details that kind of slip through the cracks. So we're given the formula CH2OH, CHOH, CHO. And carbon backbone here, we have 3 carbons. Now, when it comes to these 3 carbons, there's a couple ways to draw them. So one is just to do the shorthand, CH2OH, CHO, and then you've got your cross of H and OH. Another is to actually write them out. So we have our CHHOH. That's that carbon. We still have our OH and our H. Now this carbon has a hydrogen and an oxygen, but it's double bound to this oxygen. So if you start writing out this Lewis structure, you've got 3 in the back, 1, 2, 3. You've got an OH coming off the carbon. We're going to do a squiggly line here for the OH because we're not going to specify if it's wedge or dash. This is what you're trying to figure out. And then you've got a C, O, and an H. but carbon has to have 4 bonds. So this is where you're going to get the aldehyde at the end. Now, a common mistake I keep seeing, the reason we're having to bracket this OH is because the hydrogen is attached to the oxygen. So if you wrote CH2OH, it may not necessarily be obvious that this OH, this H here is associated with this oxygen and not this carbon or not this carbon. So if we draw the carbon down here, this is really what it looks like. Now, when it comes to setting up the priority, this is highest because it's oxygen, this is lowest because it's hydrogen. But in terms of these two carbons, we need to write out what's bound to them. Now, this oxygen double bond here is actually going to count as 2 oxygens. So even though it's CHO, we don't write it as OH, we actually write it as COOH. Because actually with the CIP rules, a double bond just counts as the same atom being bonded twice. Up here we have CO for that oxygen, hydrogen, hydrogen. And now to figure out the priorities, we compare the first pointed difference between their formulas. And we always work left to right here. I saw a lot of students yesterday trying to work right to left. It's always the first ones first. That's why we rank it in terms of decreasing atomic weight. All right, so that's it for all the questions I got asked in advance. Again, if you were in the organic lab yesterday, you are free to ask questions about this. The goal here is to make sure you have understanding of what's going on, because this is going to become important, especially as we start working our way to characterization. If you don't understand what these drawings are telling you, you're going to kind of struggle in terms of doing an analysis. Any Chemistry 1 students, you're also free to ask questions, or any people who are just kind of here, not even in my course, you're free to ask chemistry questions. So I'm going to keep the chat up for just another minute or two. If I don't see any questions in the chat, I'm going to turn off the chat. I do need to submit some, do need to do a little bit of work. All right, sorry, I was responding to an email. So, can you explain both number 6 and number 7 in the lab manual? So, number 6 and number 7, these are, one's the pentane and one is the alcohol. So we got 6 and 7. I guess I should actually verify that before I make that statement. Give me just a minute. So with the dimethylcyclopentane, you've got two CH3 groups here that you're going to tack on, and you can tack them on anywhere you want to. Now, to do this, you're going to substitute a hydrogen. Each of these carbons contain 2 hydrogens. So first option here is to do that one. Do them both in what's called the 1-1. And then you can do 1-2 and 1-3. Now you may say, well, what about 1-4? Well, 1-4 is just 1-3 with a mirror image, and 1-5 is just this one with a mirror image. So relative configuration, meaning that we're not going to specify stereochemistry, you have these three. So what you need to do from here is determine, if I put wedges and dashes in here, do I have a stereocenter? So for this one, you don't. 2 methyl groups on the same carbon, you don't have any stereocenters, so there's only one option here with 1,1-dimethylcyclopentane. With these, depending on whether you got wedge or dash, you can get a meso complex. So the relative line drawings, it's these three here, and from the different constitutional isomers, determining which of the isomers contain chiral centers, that's what you're going to figure out here to figure out if any of these carbons are chiral. And for C, the ones that are chiral, you're going to figure out if there are meso structures. You can see that by looking at the symmetry of the molecule and the different diastereomers and enantiomers. So once you figure out which ones aren't meso, figure out one form and then flip all the RS centers, and then I'll give you the other one. 6 and 7 really are kind of the same problem. Now, the challenge with 7 here is that you've got a CH3 group and an OH group. And the reason this is going to create issues for you is that here we had obvious symmetry. Here, you're never going to end up with a meso complex. So for 7, you're going to end up with a lot of combinations. So we can start with the 1-1 combination. And for all these, I'm going to make the alcohol the number 1. Then we can do 1-2, 1-3, 1-4, and 1-5 and 1-6 are just basically mirror images of 1-2 and 1-3. So you've got these 4 starting structures. You need to first identify if they're chiral structures. This one you're not going to have one chiral because it's a ring both ways. But definitely with these 3, you're going to end up with chiral centers. From there, once you've identified the chiral centers, you're going to need to figure out if there's any mesoforms. Big hint for 7, there are no mesoforms. Every single one of these is a unique stereoisomer. From there, do the different possible iterations, both wedge, one dash. So both combination of wedge and dash, both dash. Figure out which ones are enantiomers and work forward. So with 7, I would definitely say that it's 6 just with a lot more answers. But if you can do 6, 7 shouldn't be that bad. You're welcome. Meso again. So with a meso complex, there's two ways to look at it. So from the theoretical standpoint, a meso complex is one that it's its own enantiomer. So it is a chiral compound, and we do need to specify that it has chiral centers. But despite it having chiral centers, it is not actually a chiral compound. So by definition, a chiral compound must have a non-superimposable mirror image. Meso compounds do have a superimposable mirror image. And they come about from mirror planes. So the molecule will have a mirror plane. So in terms of a Fischer projection, the way we catch meso compounds is that we look at the Fischer projection and we look for an up-down symmetry with the molecule. So in this case, I've got HF, HF, two hydrogens. So there's a mirror plane sitting here in the molecule. And the reason why we prefer to do this with a Fischer projection for a linear compound is that the molecule itself isn't necessarily drawn in the most intuitive way to figure out where the stereocenters are and what the RS symmetry is. So from the Fischer projection, a meso compound is going to have a mirror plane running halfway through it. Now, what makes it meso is that if you look at these two centers here, they look the same. So one's going to be R and one's going to be S, and they're mirror images. So this is why I say it's an enantiomer of itself, is that if you look at it, the R and S are reflected across that mirror plane. Physically, what happens is that R and S have equal and opposite rotations if they are the same structure. So in this case, if we look at the top and the bottom, it's fluorine bound to a carbon with two hydrogens, fluorine bound to a carbon with two hydrogens, both adjacent to a CH2. This will rotate the light so many degrees, this will completely counteract that rotation. Now, for cyclic molecules, we're actually better to look at the drawings. So for something like this difluorocomplex, you can more easily see the mirror plane if you draw it, whereas if you do the Fischer projection, you might end up with something like this. And it's not as obvious from the Fischer projection that it's a meso compound. But this mirror image here, again, is going to have the same effect. We have an R and S symmetry reflected across the mirror plane. So technically, you could invert both of these to R and S, but when you do that, that mirror plane basically gives you the ability to rotate it over and counteract that inversion. So your meso here, again, comes about from mirror planes, but the critical point here is that it has to have chiral centers. So an achiral compound like cyclohexane has plenty of mirror planes in it, but it doesn't have any chiral centers in it. So we would never call an achiral molecule meso. But if we have chiral centers and we have a mirror plane running through it that cancel out the chirality, basically we get opposite RS symmetries for the same groups, then we have a meso complex. All right, we're getting on to 10 o'clock in the live stream. There's a live stream tomorrow from, I can answer one of this question. How would the top chiral center be chiral if it's attached to two hydrogens? So this one isn't chiral. There's a fluorine and a hydrogen, and there's a fluorine and a hydrogen here. It just may be hard to see it on the screen. So both of these are Fs, which would make this one chiral, make this one chiral. Now this here isn't chiral. So this structure here without the fluorines is definitely not chiral. We'd have to stick something in there to make it chiral. Yes, so if we have one wedge and one dash, that will get rid of the mirror image. So in that point, we definitely don't have a chiral compound. So we definitely don't have a meso compound. So this is definitely meso, but when we do the mirror image, or we flip the R and the S, this ends up not being meso because there's no mirror plane. And if we do the analysis, this is probably R, and this will also be R. This is something that you actually surprisingly can intuit. So even without understanding the theory, you can pick up on meso compounds just by looking for those mirror planes. It's kind of one of those weird artifacts of how we do this type of analysis that you actually conceptually understand this and see this. You're just not used to calling it these things. So when you see a mirror plane running through a compound with chiral centers, that's meso. You kind of intuit that there is a mirror plane in there, but you just don't know how to describe it yet. We describe it as meso. All right, so live streams are tomorrow 11 to 12, Monday 9 to 10, and then Tuesday 11 to 12. So we've got 3 more live streams between now and the lab next week. For the organic folks, you do need to finish working on those pages 15 and 16 lab manuals, submit them next week for a grade. I'll go through them and grade them, give them back to you the following week. But again, you're free to ask questions. Like, it's not like I'm not going to tell you how to do this because this is kind of foundational knowledge. The goal with test 1 is to make sure that you're really well set up for when we start actually discussing organic molecules. So the characterization and the drawings, they're all going to show up throughout the semester. It seems like a lot right now. It's because it is. It's a lot of very theory heavy, but armed with this theory, it should make the subsequent exams a lot easier to work with. So again, if you ever have questions and you can't make it to a live stream, feel free to email me in advance. As you can see at the start of this video, I try to answer them all at the start so the folks who can't make it can see it. And I will see y'all tomorrow.